Deploying a large language model into production has never been easier, but securing it against adversarial manipulation requires a distinct approach. The core vulnerability of current LLMs is architectural. By design, they possess a structural inability to strictly separate underlying system instructions from user-provided data. They process everything as continuous language. This breaks the bedrock of traditional web application security. Legacy security relies on strict deterministic boundaries that clearly separate executable code from passive data inputs. An isolated chatbot hallucinating a wrong answer is merely an annoyance, but wire that same model into your backend APIs, and you've potentially built an unmonitored remote code execution engine. Securing an LLM requires abandoning deterministic security models. Engineering teams must understand and defend this probabilistic threat surface. The Open Worldwide Application Security Project, or OWASP, has codified these exact risks in their updated Top 10 list for large language models. It is the definitive guide to the most critical vulnerabilities found in production environments. Sequential lists of vulnerabilities often feel abstract. To actually understand these threats, we have to map them directly onto the functional nodes of a production environment. This LLM architecture tracks 5 core nodes: user input, AI gateway, the LLM engine, a vector database, and external APIs. An attack bypassing defenses moves from user input, manipulates the engine, and triggers a failure at the API layer. We are going to deconstruct this architecture node by node. We will locate exactly where and why the OWASP Top 10 vulnerabilities occur. Viewing the entire application stack as a single living architecture is the only way engineers can build real intuition for AI security. This focused section of the diagram highlights the direct interface between the incoming user data, the foundational system instructions, and the LLM engine. This interface is exactly where OWASP Demo 1 occurs: prompt injection. Prompt injection is an attack technique designed to make the AI ignore its original instructions and execute unauthorized commands. In a direct prompt injection, adversarial user text overrides system instructions. Because the model cannot parse authority differences, malicious text swallows and replaces the core logic. The attack can also be indirect. In an indirect prompt injection, the malicious payload is hidden inside an external document or web page that the model is instructed to read and summarize. Attackers bypass standard language filters by encoding these injections in Morse code or by phrasing them as prose and poetry, which the system processes without triggering generic security flags. This linguistic manipulation leads directly to OWASP number 7, system prompt leakage. System prompts are high-value targets. Developers frequently use them to define sensitive context, proprietary business logic, or required API keys. Specific adversarial queries can trick the model into abandoning its guardrails and simply printing those foundational instructions back to the user in plain text. The input layer is inherently porous. It is impossible to write a system prompt robust enough to block all forms of linguistic manipulation. Moving backward in the architecture, we find the data pipelines that feed and shape the LLM's intelligence. This upstream reliance introduces OWASP number 3, supply chain vulnerabilities. Enterprise teams rarely possess compute power to train foundational models from scratch. Instead, they rely heavily on open-source hubs containing millions of pre-trained models. Downloading an unvetted billion-parameter model with unknown provenance into a secure enterprise environment creates a massive security blind spot. It is physically impossible to manually inspect the data. That lack of visibility opens the door to OWASP number 4, data and model poisoning. Injecting subtle, targeted errors into a model's training data permanently compromises its internal ground truth logic. Because the AI model is a software artifact, it is fully susceptible to malware equivalents, baked directly into its architecture long before you download it. This data risk applies locally as well, codified in OWASP number 8, vector embedding weaknesses. Enterprises often use retrieval-augmented generation, or RAG. RAG pulls specific documents from a vector database to give the LLM factual context. A cascading failure occurs when source documents inside the vector database are manipulated. The corrupted red file poisons the local context, steering the model into generating a hostile response. If the upstream supply chain or the RAG data is compromised, the LLM will confidently generate mathematically perfect, yet completely malicious outputs. Shifting focus to the far end of the architecture, we track where the LLM's generated output travels. The pathway returning to the user is the primary vector for OWASP number 2, sensitive information disclosure. This frequently occurs via a model inversion attack. A model inversion attack is a technique where an automated agent systematically queries the LLM to map its responses and extract proprietary intellectual property or sensitive patient data baked into its weights. By rapidly probing the model, attackers harvest this data and leak it directly back out through the standard user interface. The pathway moving toward the backend introduces OWASP number 6, excessive agency. Excessive agency is the severe risk of granting an LLM autonomous permissions to call external plugins, execute server-side code, or modify databases without secondary verification. Combined with downstream trust, we get OWASP number 5, improper output handling. An injected payload forces the LLM to write a SQL script. If the application blindly accepts it, the malicious gear icon executes, triggering a catastrophic chain reaction. Unchecked agency transforms an AI from a passive chatbot into a weaponized attack vector against the entire backend infrastructure. We have to look past the individual queries. Operating this system continuously at full production volume introduces threats of scale. The first is OWASP number 9, misinformation. At high query volumes, unverified hallucinations snowball. This introduces deep systemic bias and rapidly degrades the reliability of the entire application for the end user. The final architectural threat is OWASP number 10, unbounded consumption. Adversaries specifically design infinitely complex, long-running prompts, intentionally flooding the system to tie up the LLM's computational resources and block legitimate traffic. This creates a denial of wallet attack. Spiking token costs rapidly drain operational budgets and degrade service availability for legitimate users. Comprehensive operational security must protect the application's data alongside the financial and computational resources powering the AI. This is the interconnected view of the compromised system. To secure it, we must apply targeted defensive solutions across the architecture. Relying solely on system prompts for defense is a guaranteed failure. The solution requires establishing a comprehensive AI security posture management framework. It is a set of practices and tools used to continually discover, secure, and monitor all AI models, data pipelines, and configurations across an organization. The first mandatory shield is deploying a dedicated AI gateway. This gateway intercepts malicious prompt injections before they ever reach the model and actively redacts sensitive data before it reaches the user. The second shield protects the infrastructure pipeline. Teams must implement strict provenance vetting for all supply chain models and apply rigorous access controls to the vector database. The third shield strictly limits the LLM's permissions to external APIs, stripping it of excessive agency. The cardinal rule of AI application security is absolute. All LLM output must be treated as untrusted, malicious user input before it is allowed to touch a downstream database or execution environment. The OWASP Top 10 maps the structural vulnerabilities inherent to large language models. Deploying enterprise AI requires an architectural shift away from deterministic trust and toward continuous probabilistic verification. By understanding this interconnected threat surface, engineering teams can lock down their architecture, ensuring their AI remains a powerful asset rather than an open door.